on that. I will just go through two examples. The algorithm itself has just one line, but I advise you to try some examples to make sure you fully understand that. Now to put everything together, we're going to look at how the scanner generators work. Remember, each of you wrote a scanner by hand, manually. In reality, because that's for learning purposes. Okay, typically, in your first year compiler course, students are normally asked to write a scanner by hand. You're going to see reason why. Because if you want to implement a scanner automatically by using a scanner generator, you don't have to do anything. All you have to do is just to define all the tokens by giving their corresponding regular expression. That's it. Then the scanner generator will give you a scanner. Okay? Even though we haven't written a scanner by using a scanner generator, nobody is going to stop you from doing that when you leave your stuff. So that after today's lecture, you should understand pretty much how scanner generator works. And you should be able to write a scanner generator yourself, because it's everything that's needed for implementing a scanner generator will have been introduced by the end of today's lecture. You take a regular expression. I'll use a tiny example to show you how it works. Okay, that's the word. So that's the example. You saw in the second lecture of first week. By now you might have forgotten. It doesn't matter. Okay, what's important to know is that if we are given that regular expression, if we apply Thompson's construction algorithm, we're going to get the following equivalent event: non-deterministic finite automaton. It is non-deterministic because we have epsilon translation. So that means if the machine starts from the start state, it can move to 1, it can also move to 5. Once it at 1, it can move to 2, it can move to 10 without reading anything from the input. Remember the analogy I gave to you guys in the second week. So if this is a finite state machine used for a vending machine, you put coins inside, one means just $1 or whatever. So epsilon means the machine can make transitions without taking any coins, from you. Okay, it's just make moves. Okay, that's not deterministic. Of course, a finite state machine is not deterministic when you have more than one transitions from the same state on the same input symbol. For example, here we don't have that. For example, from here, we already, if the next input is 1, we can go from 5 to 6. If you have another transition from 5, let's say, to 15 on the same input 1, that's also not deterministic. Sometimes we like it, what we learned in the second lecture. But whether you know that or not really doesn't matter. Okay. So the point is, here is an EFA, and we don't like it. We want to get a DFA. Okay, a DFA is a special case in which, firstly, we don't have epsilon transitions anymore. Secondly, whenever you are at one state, you want to move to another state, okay, on a given symbol like 1, you can only have one transition labeled by 1. Okay? When you start from any state, okay, you have one transition on 1, another transition on 0, but you cannot have 2 transitions on 1. Okay, that's not deterministic. Okay, so we're going to apply subset construction algorithm. So that the exam is like about 3 weeks away. So pretty much, I'm here just trying to solve a question that's definitely going to appear in the exam. Okay, so if we're given this EFA, how we can get the equivalent here. I will show you the solution that I go through the algorithm. I don't really read the algorithm because you can read yourself the timeline. Okay, it's very simple. Okay, now it's called the algorithm that takes this EFA and produces the equivalent DFA is called subset construction. You should have already now guessed why the algorithm is called subset. Because if you look at the DFA, every step here is a subset of the states here. Here we have states labeled from 0 all the way to 50. So we have 16 states. So in the equivalent DFA, every state is a subset. Okay? And this guy is deterministic. Number one, you cannot see any epsilons anymore. No epsilon transition. And also from every state, there are two transitions. One on 0, one on 1. Okay? So that means the transition is always deterministic. Okay, if you are in this state, if the next input is 1, you can only go here. There's nothing else you can do. Okay, so every state has two transitions. One labeled by 1, another labeled by 0. So it's deterministic. So in the worst case, there can be 2 to the power of n states. Okay, so that means in theory, a DFA can be larger because that's just a power set. However, in practice, a DFA is normally smaller. I mean, for many practical applications. So that's why in many real-world applications, we typically convert EFAs to DFAs because DFAs are smaller and more efficient. However, in the theoretically worst case, DFA is less efficient, but that normally doesn't happen in practice. So I normally wouldn't go through this. Okay, normally you introduce the algorithm, you have all the notations, and once you have seen my working out of the example, you should be able to understand that. For example, epsilon closure is just like you start with a state S. Epsilon closure just gives you the set of states you can reach by following only epsilon transitions. So here is the same definition, except this is T. T is a set of states. So you start from set of states, okay? It includes all the states you can reach on epsilon transitions. So move TA means if you are in a set of states T, if the next input is simple as A, what is the set of states you can reach? Okay, don't worry about it. Okay, when you look at the example, and you revisit this slide yourself, everything will become clear. This is the algorithm for the subset construction. Set of states T, if the next input is simple as A, what is the set of states you can reach? Okay, don't worry about it. Okay, when you look at the example, and you revisit this slide yourself, everything will become clear. This is the algorithm for the subset construction. Again, it doesn't make much sense just to read this line by line. Okay, so I will just follow this algorithm, convert that EFA into the DFA you saw, and we come back. We spend maybe just less than a minute on it. Okay, you will figure this out yourself. Okay. I haven't done much yet. So basically, we're going to look at how the subset construction algorithm works. I haven't read the algorithm yet. I'm just going to go through this by using example. Okay, see how we can convert this into the DFA to solve it. The algorithm is very simple. It says before I do that, it might be a good idea if I just say a few words first. So this is the non-deterministic version. So this is a deterministic version. So basically, the basic idea behind the subset construction is for the TFA to simulate deterministically what the AFA does non-deterministically. For example, in the TFA, you start from 0. And if you don't read any input will only have two symbols, 1 or 0. If the machine doesn't read anything, just think about my analogy. You haven't put any coins into the vending machine. If you haven't done that, the machine can arbitrarily make moves already because there are epsilon transitions. Machine can be at 0. You can also choose to move to 1. You can also choose to move to 4. Once it's at 4, you can move to 15. You can move to 5. You can also move to 10. You can also move to 5 from here. Okay? So essentially the machine can be in any of those states without reading anything from the input. Non-deterministic. One of them. Okay, so it's 0, 1, 2, 5. So basically 0, 1, 2, 5. Sorry, not 4. 0, 1, 2, 10, 5. This guy says, look, this is my start state. I simulate exactly how you do non-deterministic. So I will start with a set of 5 states. This will be all the states you can be without reading any input. So that's pretty much how it works. Then, if the next input is 1, the DFA guy will say, look, you can be only in one of these 6 states. Okay? So if you look at the machine here, so if the next input is 1, you can go from here. You can reach 1. Once you are at 1, you can go to 6. Sorry. From 5, you can go to 6. Once you are at 6, you can move to 9, you can move to 7. And there is also 1 here. Because with the next input is 1, you can reach 11. Once you are at 11, you can reach 12, you can reach 14, and all these states. Then this guy says, look, this will be all the possible states you can be in if the first input you read is 1. And that's it. So this guy pretty much simulates how the DFA works non-deterministic. But anyway, if I move along, you will understand anyway. So let's just go back to this slide. Okay. So we're going to apply subset construction algorithm to get a DFA from the corresponding EFA. We always start from the start state. So I have just written down at 0 because 0 is a start state. Okay. Now, according to the algorithm, before we try to add more transitions, we need to build a so-called epsilon closure. So what that means is we immediately include all the possible states we can reach without reading anything. That means by reading only epsilons. Well, if you look at the TFA, AFA,
kind of awesome.
From 0, we can reach to 1. So once we are at 1, we can be at 2. Once we are at 1, we can also move to 10 on epsilon. And we can also reach 5. Okay. So this is a set of all the possible states the AFA can reach on epsilon transitions. So that's the first step of the algorithm. Start from 0 and 0, add all the epsilon sort of states reachable through epsilon transitions. That's it. Right? Then we start adding transitions by creating more states. Then we say, okay, so that's just make sure we haven't lost anything. 0, 1, 2, 3, 10, and 5.
This is going that way. So
and then we say, okay, so if the next input is 0, so the TFA is in this state, if the next input is 0, what will be all the states we can reach? Well, you just examine all these 5 states one by one. Now you look at 0. So if you start from 0, is there any transition level 1, 0? No. Okay, you ignore that. Now you look at step 1. If the AFA is at step 1 is 1 by 1 by creating more states. Then we say, okay, so that's just make sure we haven't lost anything. 0, 1, 2, 3, 10, and 5. That's it. And then we say, okay, so if the next input is 0, so the TFA is in this state, if the next input is 0, what will be all the states we can reach? Well, you just examine all these 5 states one by one. Now you look at 0. So if you start from 0, is there any transition level 1, 0? No. Okay, you ignore that. Now you look at step 1. If the TFA is at step
does 2 go anywhere? Oh yeah, 2 goes to 0. 1 can't go anywhere. 0 can't go anywhere. Oh, okay.
we have any transitions?
Then we just do it for each. So 3, what does 3 go to? Oh, but 3 can go to epsilon. So it can also go to 4. And it can also go to 5. Whoa, did not meant to press that. Yeah, then you go for 1, and then 1 can go back to 2, and it can go back to 10. What the heck? That can't be right, anyway.
From 1, labeled by 0, nothing. 2, there is 1. So if the ASA is satisfied 2, we can go to 3 along this transition. Now we just write down 3. Then we look at 2. So if the AFA is at 10, can we go anywhere along 0 transition? No, because there's only 1 transition level. Then you look at 5. Nothing. So that's it. So what that means is, if the AFA is in any of the 5 states, if the next input is a 0, what will be the state you can reach directly? The answer is 3. Okay, have I missed anything? So 0, 1, nothing, 2, 0, 3, 10, 5. But now we cannot stop there, because once the AFA is at state 3, it can move to any other states along epsilon transitions. Then we simply just build a closure of that. Okay, what we are doing is we look at the 3. If the machine is at 3, it can reach 4 along this epsilon transition. So that means we can go to 4. So we can go to 4. So we can, once we are at 4, we can go to, once we are at 3, we can go to 4. And once we are at 4, we can also go to 5. Okay? But once we are at 4, we can also reach 1. So once we are at 1, we can also go to 2 or 10. Okay. Now, this will be the set of all the possible states. The AFA can reach non-deterministic. That means AFA, as soon as having read input 0, the AFA can be in any of those 6 states. And well, that's, you already know the algorithm. You're pretty much doing the same thing for everything else. So now you just have to look at 1. Right? Because we have done the transition on 0. Now we need to see what will be the state this guy can transit to if the input is 1. It's the same process. So the algorithm Caroline saw before pretty much just works this way. Then again, you examine all these states one by one. You look at 0, you look for the transitions labeled by 1 only. You start from 0, there's nothing labeled by 1. You look at 1, there's nothing. You look at 2, then you look at 5, there's 1. So once interface at 5, you can reach 6. So just put 6 in. And 10. So if the machine is at 10, it can move to state 11 along this transition labeled by 1. Okay. So that means if the next input is 1, the machine can follow a transition labeled by 1 to either 6 or 11. But that's not all, because the machine can also move any along epsilon transitions non-deterministically. You pretty much just do the same thing. Let's call it closure. You just close it, right? Close it by adding epsilon sort of a transition reachable states. You look at the 6. Once you're at the 6, you can go to 7 along epsilon transition. You can go to 10. If the machine is at 11, you can go to 12. You can also go to 14.
Mm-hmm.
11, you can go to 12, you can also do. So that's about it. So basically that's
oh, you can also get 12. Did I miss that? The heck? You can also get 14.
the set of states the machine can be if the next input is 1. Okay? So I just do a little bit more. This, I don't have no use to project here even if you cannot use it. Okay. Well, so now patient needs.
Sure, if you want me to make it, I'll make it. So from 11 going to 0, there is no 0 transition. From 12, if we use 0, we can get to 13. From 13, we can also get to 14. And we can also get to 12. Interesting. Anyway. Okay, now from 14, where can we go with 0? We can't go anywhere with 0. From 6, where can we go with 0? We can't go anywhere with 0. From 7, you can go to 8 and 0. And 8 also gets you to 9, and 8 also gets you to 7. And since 9 is in the fray, you change it like that. And we do 9, and 9 can't do anything from 0. Okay. So we try 1. So 11 to 1, no such thing. 12 to 1, no such thing. 14 to 1, you get 15. And then from 15 you get 4, and then from 4 you also get EPS, you also get 5, and you also get 1, which 5, and then from 4 you also get 1, and then from 1 you also get 2, and you also get 10. Okay, that is 14 done. What else we got? 6. Can't do anything with 6. Can't do anything with 7. Can't do anything with 8. Can't do anything with
9. From 12, we're going to go to 13 along this 0 level transition. And 14, nothing. So that's it. So what that means is, if this interface is in any of these 6 states, if we read the input 0, we can reach one of these 2 states. And immediately you add more states you can reach through epsilon transitions. Now we just look at them one by one from A. So once we are at 8, we can reach 9. Once we are at 8, we can also follow this one, we can reach 7. If we're at 13, we can reach 14. And we can also reach 12. Okay. So I'm just now we look at the state, and this guy can reach through a transitional one. Okay. It's the same story. You can just bit of fortunate all this together. But anyway, we're looking at these 6 states. We're looking for the transitions leveled by 1, 6, 11, 7, nothing, 9, no, 12, 14. Yeah, there's only 1. Is that correct? 6, 11, 7, 9, 12, 14. Okay. So we can go from 14 to 15. Okay. So if the interface is at 15, we can add all the states again. We can reach through epsilon transitions. So just look at this graph. We got a 4. Why we can reach, let's do this one. So it's the same story. This time we're looking at the state we can reach through input 0.
Okay, if you want me to do it, I'll do it, but like it seems like I'm just doing the same thing over and over again. 13 to 0, can't do anything. 14 to 0, can't do anything. 12 through 0. Yeah, but if I go 12 through 0, it's just gonna do the same thing, because this did a 12 through 0. Whatever, I'm just gonna give you 13. 13 produces 12 and 14. 8 through 0, can't do anything. 9 to 0, can't do anything. 7 through 0 gives you 8. Which gives you 9 and 7. Wow, these are equivalent. Crazy. How do I...
Going 8, 13, 9, from top. So the next input is 1. What would
Okay, I see how it is. What can you get through with 1? I don't know, let's find out. So from 13 you can't get anywhere, from 14 you get to 15, from 12 you can't get anywhere, from 8 you can't get anywhere, from 9 you can't get anywhere, from 7 you can't. So 15, wow, this is the same as this. You're crazy.
from 4 is on 0. So that means from this guy.
Okay, now you're gonna try this one. Through 0. Okay. Okay. 3 through 0, nope. 4 through 0, nope. 1 through 0 was 1 through 0, nope. 5 through 0, nope. 2 through 0, yeah, we get 3. 10 through 0, nope. So we just get 3. What can you get with 3? You can get 4. You can get 5. You can get 1. You can get 2. You can get 10. This is really close to this. It's just it starts at a 3. This starts at a 15. Okay. I'm gonna leave that hole for now. Let's go through 1. Okay. Three to 1. There, nope. 4 to 1, nope. 1 through 1, nope. 5 through 1 gets you 6. Okay, 2 through 1, nope. 10 through 1 gets you 11. Ooh. So 6 and 11, which gets you 11. Okay, I think that's the same as this, right? Wait, are we done? Oh wait, no, this one needs to produce one more. Let's see what you produce. Okay, so 0. Okay, so 3 to 0, where can you go from 3 to 0? Nowhere. 4 to 0, nowhere. 5 to 0, nowhere. 1 to 0, nowhere. 2 to 0 gets you to 3. And 19, what the what? Ten through 0 gets you to nowhere, so this is actually just a self-reference. I'm pretty sure. I feel like if I could make this arrow more curvy. Let's try 1. How does 1 go? So 3 to 1, no, nothing. 4 to 1, nothing. 5 to 1 gets you 6. through 1, nothing. 2 through 1, nothing. 10 through 1 gets you 11. And 6 and 11 is the same as this one. I think we're done. Nope, we haven't done this one. Okay. So let's do a 0. What is 0? Good job. 15 through 0, nothing. 4 through 0 is nothing. 5 through 0 is nothing. 1 through 0 is nothing. 2 through 0 is 3. Okay. Definitely wrong one. Two through 0 is 3. And 10 through 0, there is nothing. Oh, so this is just this? Okay, so let's try 1. 15 through 1, nothing. 4 through 1, nothing. 5 through 1 gets you 6. 1 through 1 gets you nothing. 2 through 1 gets you nothing. 10 through 1 gets you 11. Okay. Nice. I'm happy with that.
Then from 10, we go step, we can do 3, 4, 5. 3, 4, 5. Once we're at 5, we can go to 10, we can add okay. So that's it. Okay. So if we start, with this FA, we can apply subset construction algorithm. We can get an equivalent DFA. So this is the DFA. Okay. Now, as I said, I'm not going to spend time on this. Once you have followed, this example, I would expect you just maybe 2 minutes to understand this. If some closure S, 0 is S, you just add all the steps you can reach through epsilon transitions. Epsilon P is a set of states. Okay? So basically, if you look at my demonstration, P is just the set of red numbers. every time you have obtained that T, you need to build a closure. That closure includes all those in dark color. What is move TI? Well, you saw what I did. Every time I just draw a 0, we're going to move from here to there. Okay, that's what you do. So if you look at the algorithm, something you can understand if you understand this example, that's exactly what we do. Look at the first line. Let S0 be the start state. In our case, 0. Firstly, build a epsilon closure for that. Well, we did that. Okay? This is the S0 closure. Anything you can reach through epsilons. Once you have done that, you enter into a while loop. What does the loop say? It says you just work on every state you haven't finished so far one by one. So what do you mean a state is not finished? Okay? Because according to this example, our alphabet has 2 symbols. So that means every state must have 2 transitions. Okay? So a state is called finished or marked if and only if you have found its 2 transitions. If you haven't, it says you just keep doing it. That is exactly what we did. Okay? From here, we go there. Then since this guy is not finished, we keep adding more transitions until eventually every state has 2 transitions. That's pretty much it said. Okay? You can look at the algorithm yourself. That's pretty much this. Okay? As I said at the very beginning, because I'm going to release a few possible examining papers tomorrow after we have finished tomorrow's lecture. Every year we have a question on this. People normally get the marks for this one. It's just a straightforward application of the subset construction. Now, there's something I haven't explained. So, by applying the subset construction algorithm, we get a DFA. But you might be wondering, hey, did you say in week 1 you have to define a DFA precisely? A DFA has 5 components. How do we define that? Well, this is the definition. You start from AFA, you obtain a DFA. Precisely, what are your 5 components? It says the DFA has the same alphabet as the AFA. Okay, in the AFA, the alphabet has 0 and 1, 2 symbols. Okay, if you build the corresponding DFA, you also have 2 symbols, 0 and 1, no more, no less. What are your states? Well, all the states here, 5, because you talk about 5 components used for defining a DFA. Now, what is the start state? Well, the state that contains the original start state. If you look at the original AFA, this guy is the start state. Well, that guy contains 0, this must be the start state. So that's it. The next question is, what are the accepting states? It says, you look at every state you have created. If a state contains an original accepting state, then that will be accepting. Now if you look at the original AFA, we have 1 accepting state. Now you look at your DFA, for any state that contains 9, that must be accepted. And that makes sense, because we are simulating how the AFA works. Okay? As long as we can reach that accepting state, of course it has to be accepted. Okay? So that's that one. What are the transitions? Well, by construction, we have already created all the transitions. Okay? So the transition is obvious, alphabet is obvious, state is obvious, because once you have done everything that you can. And the start state is the one that contains the original start state. A state is accepting if it contains 1 accepting state from the AFA. Because in our example, there's only one acceptance. Okay? There can be two, there can be three, it doesn't matter. Okay? You look at your AFA, as long as anyone that contains at least one accepting state, that must be accepting state for the DFA. Okay? So that's it. Any questions about the work? So that's what I said. It might be good if we talk about it. The EFA to DFA construction because it's fresh. The exam is only a few weeks away. Okay, once we have done that, this is the algorithm. I'm not going to spend my time on. Okay, it's actually just one line. Okay, I will explain the idea.
That is not one line.
And you can read it yourself. Okay, so what are we talking about here? So the problem we want to solve is, once we have obtained DFA, the natural question you would like to ask is, can we get is it possible to obtain DFA with the minimum number of states? Is that possible? The answer is yes. The algorithm does that. So how do we do that? Well, again, I'll show you the solutions. I'll show you how it works. See, this is EFA we have obtained. Okay? In order for us to talk about that more easily, we are going to label the 5 states by using a letter each. Otherwise, it's very hard to refer to them. So we just renamed all the 5 states. This is A, B, C, D. A, B, C, D, E. It's the same DFA. Now, if you apply the state minimization algorithm, you actually obtain a DFA with only 2 states. That does exactly the same thing. Now, how do you do that? Now, here's the algorithm. This is algorithm that belongs to a class of so-called optimistic algorithm. Of course, you need to prove it's optimal, but that's not something we care here. The idea is you start optimistically, okay? Because we want to find a DFA that has a minimum number of states. Now, what can be the minimum number of states for this particular case? You start by making a guess. You would say, okay, fine. In this DFA, at least there are two types of states. Those non-accepting, which is A, B, D, and those that are accepting, because we have two accepting states. Certainly, if you think intuitively, you need at least two states. Because why accept out 1,000? Obviously. Like,
you call this D. You call this C. And this one you still and you call this E.
equivalent DFA, right? So in the minimum case, you need to have just two. Okay? This is an optimistic assumption. If that's the case, you can easily obtain a DFA by simply just collapse all the corresponding edges, you will see. Okay? But this could be wrong. Now what do? And you just go through this algorithm. This one. He says you start by dividing your states into two sets. One containing final states, one containing non-final state. Then you enter into this loop. They keep doing the same thing. Yeah, what do? This is what you do. Because we only have two simples. You test to see you for each of these, for any of the states so far. This is like a partition. Okay? For any of these partitions, you do the same thing. Let's say we deal with the first one first. Okay? Now, there are only two input symbols, 0 and 1. We just test to see if the next input is 0. We start from any of these three states. What will be the next state we can reach along the 0 if the next input is 0? Okay? Say, we look at A.
A from 0 gets you to D, D from 0 gets you to D, and E from 0 gets you to D. Okay. How about A from 1? A from 1 gets you to B. D from 1.
So if the next input is 0, we can reach D. We just say, okay, if the next input is 0, we can reach D. Now we look at D. So if the next input is 0, where can we go to? We stay at the same state. So that means we stay in the same state D. Now look at E. So if the next input is 0, we go to D. Now, according to the algorithm, what this means is, so far so good. We would like to merge all those equivalent states. Okay, now we check to see if the next input is 0, what will be the states we can reach? where they all be, where they all reside in the same partition. Okay, as you can see, no matter whether we go from A to D or we loop, at the same state D or move from E to D, but we start from this partition, we always end up still staying in the same partition. Okay, so that means these three guys should not be split. Okay, then you're pretty much doing the same thing. You just say, well, what about if the next input is 1? And you test that too. Okay, so if the next, you do pretty much the same thing. You say, okay, if the next input is 1, from A I move to B. Now from D I'm going to move to B too. Now if the next input is 1, if I'm at E, I'm going to move to B as well. Okay? Now it doesn't matter that I move to B or C. So that means if the next input is 1, we always move from this partition to our identity. So that means if you merge all the three, you're not going to put any information. So that means so far, that means these three guys are equivalent. Okay, there's no point of having three separate states. Okay, that's the idea of this algorithm. Then you do the same thing. You just say, you repeat the same thing for this part. Okay, see, now we look at the algorithm. Now we look at the algorithm. All this is saying is you have many partitions, you take one partition, you just repeatedly do what I'm just explaining to you. Okay, for every input sample, you do the same thing. You see whether they always transited from one partition to another partition. And let's finish it. Okay? So where is my Windows?
What? You didn't show us the error path.
Remember we have A, D, E, 0. So we don't have to split this guy. B, we can still, let me just clarify, it doesn't matter which E or not, as long as we always go from one partition to identical partition. That means these two states should be also staying in the same partition. That's it. So what that means is we test, we sort of apply this minimization algorithm. We start with the optimistic partition, and there's no way we can split that. Okay? The minimum state here they should just have two states. Now we add all the transitions. It's very easy. Just look at from A to B there is a transition. From A to B there is a transition, just that one. So from A to B there is a transition on 1, then you just add a transition. Now from A to D there is a transition on 0, 0. Okay. Then from B to E there is a transition on 1, from B to E there is a transition on 1. And from C to E there is a transition on 1, the same thing. From C to C there is a transition on 0. You just add that. So pretty much you look at every transition originally, then you just add the transitions for this guy, and then eventually you get this. Okay? as you can see now, I don't know whether how much you can remember what we talked about in the second lecture. That is the TFA we start with. Okay, so this is the TFA that accepts all the number of ones. Okay, you start from here. Every time you see all the number one, you move to here. Okay, as long as the number one is even, you move to here. Okay, as long as the number one is odd, you move to this. Okay, so whether you do it with 2 states, you do it with 5 states, it doesn't change the fact that both machines accept exactly the same language. It accepts the set of language such that every string has an odd number of ones. Okay? Now, just to give you another example, just to fully understand this algorithm, as I said, you can you can read this algorithm yourself, okay? Just give you another example. Okay. So here I'm just drawing a very small DFA that accepts only one string, 2 zeros. Okay. Now, it's fairly obvious you really need 3 states. Now we try to apply this algorithm to see how we eventually will end up getting this one as the minimal state event. So we start by being optimistic. Okay. We divide the 3 states into 2 partitions. One contains the 2 non-accepting states, AB. Other one contains the accepting state. And we just follow the algorithm. There's only one input symbol. Okay, we try this one first. So if the next input is 0, from A we go to B. Now, if the next input is 0, it will happen to be at B. As you can see, we go to C. Okay, so that means initially we start by grouping these 2 guys together, but they really shouldn't be together. Because if the next input is 0, one stays in the same partition, other guy wants to move to a different partition. And intuitively, this means they are introduced to represent different types of states, okay, to distinguish different types of states. That means A and B must be split. That since they go per way. Then you split them. You say, well, they cannot be together. Then you divide that in 2 more groups. Well, you don't have to go any further because now each partition will contain 1 state. Now we're done. So what is the minimal state VFA? The original. Okay. So I want you to think about that. I mean, if you want to see, that's pretty much. We are not here. This is not a proof. Okay. Here, I just want to emphasize this in compilers in some other areas as well. So there are many sort of optimistic algorithms. You start being optimistic, but that happens to give you the optimum. Of course, you need to prove that. But we are not here in the business of developing a proof. Okay. So just to summarize. You start being optimistic, you divide your states into 2 partitions, one containing non-accepting states, other one containing only accepting states. Okay? Then you take any of those partitions, you do exactly the same thing. Okay? For any of the input symbols, you do exactly the same thing. You look at the transitions, where they are going to. Okay? So if I want to show you a picture, I think I'll explain this well, I believe. Okay, this is your partition. Okay, if this few guys going to that way, this few guys going this way, this few guys going to another way, then you can split them into 3 partitions. Okay, they're simply just 2 stack together. Okay, it's almost like a tourist group. Okay, if you want to visit the same places, of course you stay in the same tourist group. If you want to visit different places, you just go your separate way because different interests. Okay, this is the same thing. Okay, just to summarize, this is a slide. Yes. While loop. For each group in the partition, it's here there is a loop for all input symbols. It's like a hidden loop. Oh yeah, it's sort of it's sort of here implicit because every time you split, you need to replace that, put it back into new. See, you remove from this, if it doesn't end up being split, it's removed. If it's a split, you put it back into this primary, you can do it. So that's already the termination condition. Once you split, you need to remove the original one and put the 2 new ones back. So you start with one group, you partition that into two separate groups, and you, in this algorithm, you don't really maintain any transition agents across the groups. You simply just test each group individually. If you don't split that, you throw it away. If you split it, you replace that with its partitions. Now it should work sort of, eventually you will reach a fixed point. That means nothing changes, so the eventually all remains. But anyway, we'll get to this also at the lecture. Let me just say a few words. Maybe we have a short break as this. After the break, we can finish maybe in half an hour. It's up to you. So this is the slide we did before. We start with the regular expression. We can obtain the EFA by using Thompson's algorithm. Then we can get a DFA using subset construction. Then we can obtain minimal step DFA. There's always an examination question like that every year. Just make sure you can do it. We have finished in half hour. Do you have a break? Do you want a break or you want me to do this? Doesn't matter. All right, maybe just keep going. Because there's so much left. Because the problem is, I want everybody to understand at least the rationale behind doing these two lectures. I think it's important. Every computer science student should have a good understanding about regular expressions, DFA and EFAs, scanner generators. These are very simple tools, and you should be able to write one yourself. Okay, in your production environment, let's say you graduated from here, you happen to write some sort of analyzer, lexicon analysis. I'm sure some of you people will do that, especially AI is getting popular. And you don't have to write by hand. You can always maybe use a scanner generator. So having done all these two lectures, so we should be able to understand the principle behind these tools. How many tools available? So the basic idea is this. So you want to use a scanner generator to generate a scanner for you. You need to give a specification. Typically, a specification has 3 parts. You personally have written some code, and on the top, the scanner generator will just copy that into the generated scanner file. It's not going to change that in any way. Directives, you will see what that means. All you have to do is just to define all your tokens using regular expressions. So that's it. Just to show you the example. Because once you have done that, scanner generator will take your regular expressions, build an EFA, DFA, minimal step DFA. Then it's going to generate a sort of table-driven implementation for doing lexical analysis. To make this concrete, you see an example here. So as you can see, there are 3 sections. Whatever you write on the top will be dumped into the final scanner implementation. These are so-called directives. Just give you a way to define some, calculator, figure all that stuff. Here will be your regular expression specification. Okay, you pretty much tell the scanner generator, I have 4 tokens. Okay, in my example, only 4 tokens. A keyword if, and less than, and less than equal to, and ID, identifier. Basically, this is your regular expression specification. Okay? A regular expression specification for if, we just if. Okay, this is very simple. How do you specify identifier? Start with the letter, followed by 0 or more letters or digits. Now you tell the scanner generator, every time you find that, return me a token representation. Remember that's what we did. Okay, I want a token representation. Give me the spelling, where you find this in the file, the composition, all that stuff. That's it. Of course, there are some rules assumed. Remember, the longest prefix. Okay, as you take a look at this, for example, if matches here, if also matches here. So basically there are 2 rules. So if you have 2 patterns, making the same token, the first one is used. So that means wherever you find an if, return it as a keyword instead of ID. Second rule says find the longest token possible. So that means if you see these two together, return me these together as a token. Not less than and equal just makes it there. So pretty much what we did before. Okay, that's it. So that's why I did not ask you to write a scanner using a scanner generator, because you wouldn't be doing it. You pretty much give the regular expression, and for learning purposes, you don't learn much. Now, once the scanner generator gets your regular expression, what do you? Oh, I have to show you the code. This is just like an abstract representation. Yeah, it's not written. Okay, I will show you the code later. This question is how do you get that? Obviously, this is just like a introduction for that idea. So you have to provide code. You will see that in a few minutes. Okay. Now, the scanner generator, everything like that, what we have learned. For the second lecture, we one, and today's lecture. So it's going to do the EFA for if, EFA for left side, EFA for that guy, and EFA for ID. Then it's going to combine them this way to get a single EFA. What that means is, if you call me to return the next token in the input, non-deterministically, I can either go there, go there, go there. Okay? I have to find one, I don't know which. So that's exactly what it means. Now, for our example, that's how it looks like. EFA for if, 3 steps. EFA for that guy too. If, that. Here, we try to use so-called character classes because it's very typical in production scanners to use so-called character classes. Otherwise, you got to have 26 letters, 10 digits or that. It's just a waste of space. Here is more compact. That letter means, one letter. Okay, you have one transition. So that makes sense so far. So what that means is, if you call me to return the next token in the input, non-deterministically, I can go to any of these EFAs. Okay, of course, I understand these two rules. Okay, so if the input is if, I'm going to treat this as accepting, not this one as accepting, because if is listed earlier. And of course, I'm going to find the longest possible. If it's less than followed by equal to, I'm going to identify return this 2. That's exactly what we did in assignment 1. I wouldn't spend time doing this here. Remember the subset construction algorithm we just learned like 40 minutes ago? Now the scanner generator is going to take that and give you a data. If you look at this, makes sense. It says, look, 01469, it's all merged. You start from here. So if the next input is less than, you go to 57. Why? Well, look, if the next input is less than, you obviously go to 57. If the next one is equal again, you go to 8. So that means even though when you see less than, it's already accepting, but you cannot accept that. Because you need to return the longest possible. You have to keep going until you are here if the next one happens to be an equal sign. That's sort of showing explicitly. But anyway, it's something you should know by now. So that's the data. But you don't really represent the DFA in memory because there's a graph, and you don't have normally a good representation of a graph. Normally use a matrix. So here is just an equivalent representation of that DFA. I don't have to project it, but let's just see a few. So if we start from this state, so basically here we list all the states. Well, we have this many, 6 states. Here we list all the input symbol. We have used character classes for it. Now, if we start from here, if the next input is I, we're going to trace it to 2 times. If we start from here, if the next input is I, we're going to trace it to 2. So if we start from here, if the next input is less than, we're going to trace it to here. Well, that's exactly the same. So basically, it's a two-dimensional array representation of this DFF. Obviously, you see a lot of blanks. So every time you end up in that blank, that's an error. That means that's not part of token, right? So that is just a two-dimensional array representation for the DFF. Yeah. Now, what is the scanner? I mean, in theory, there's not any lines, but if you look at the actual scanner generator, it has 1,000 lines of just for indications. But conceptually, that's what the implementation is. All these guys are doing is basically saying, you start from the start state, you keep making your transitions until you eventually can go any further. Okay? So I'm going to try a few examples and you should be able to understand it. So if the input is less than or equal to, right? So what do? We start from initial state. What this means is just made up look at this table. So we start from start state. Remember, in our scanner, we have a current chart, which is pointing to this. I don't know how rusty you are, there's a current chart always pointing to the next character you need to process. So this is where the current chart is. You start from here, you can make decisions. So now you can see this. Now just look at the table. I'm going to move to 5.7. Once you have moved to that, and the current chart is not pointing to there anymore, the current chart is going to point to equal sign. So now, so the next input is equal. Just look at the table. If it's 5.7, next input is equal, you put 8. Okay? Now 8 is actually an accepting state. Suppose we have another one somewhere here. I mean, obviously these 3 together is not a token. Now you just say if we're at 8, next input is equal sign, look here. It's a blank. What that means is that's an error. What the error means is these 3 together cannot be a token. Okay, what do? This, well, you just go back to the most recent accepting state. That will be the token accepted. How do you go back? Well, the implementation wise, I will say in 1 minute. So essentially, now we are here. Now we know if we are at step 8, if the next input is equal sign, there's no way we can consider anywhere. So we stop. We must find a token. And what's the token found? Go back to the most recent accepting state. Well, it has to be this guy. 5.7. Okay. In 5.7 we have accept. It's actually 8. It's 8. Yeah. So here we cannot go any further. Okay. There's nothing we can go to. Then we go back to the most recent accepting state 8. Now we have been accept these 2. There's 1 token. When the scanner is called again, we're going to start doing exactly the same thing from the start state with the current chart sending to the 3rd character. That's exactly how our scanner works. Okay? So now, if you look at the algorithm, that's what it says. Start from the start state, keep making transitions until you see a blank space, then you quit from the loop. What do? You backtrack to the most recent accepting state. Okay, that's the one you should accept, then done. That is how we call it again. I'll come back to this in a bit. Now, so this will answer your question, how do we define the spelling? So if you want to use a scanner generator, in the top section, you can have any code you like. This will be copied into the scanner generator. This will be the place for you to define how to maintain basically a token representation. That's pretty much the same as we did in assignment 1. The index is the ID. Remember, every token has an ID, number from 0, 1, 2, 3. So that's the token ID. That's the setting. The number, that's the beginning and ending columns where this token is from. So this is the structure you define. Okay. Now that's followed by your directives. You say what is a letter? This happens to be called alpha. It's just a letter, digit. What is a fraction? What is exponent? What's white space? What's a string? What's the comments? Look, this is a very complex regular expression. It doesn't matter. That defines what, because this guy allows nested. You have a slash, star, followed by two closing, the star slash. It doesn't matter. It's just allowed here. So you define all that. Your regular expression. You say, wherever you find a boolean, that's my token. Return me a token representation. This guy's ID is 0, YYX, YYX. Remember? See here? Stay funny here. Basically, just return me the line number, the spelling you find here. As the details I will explain, you can find many implementations online. Now, if you find all the keywords, that's what you do. You find plus, just give me a plus. Yeah. Now, if you find a white space, see here. That means no code, just read away. Here we need to find the comments. Since we allow nested comments, now we have to count how many, opening sort of a comment operator we have found. But anyway, just the implementation details. Once you have found all the comments, do nothing, just throw them away. No code here. If you find a string, return me the string. You find an integer, say plus, one or more digits, give me an integer. Here is where we define the group input value. Just to know that this is a value. So a float value, a token is a floating point value. It's defined as one of these three possibilities. Well, I just copied this here. That's 1, that's 2, that's 3. It's pretty much exactly I just copied from. Okay. So, you can see, so that's the first one, second one, third one. First one, second one. Now, that's it. So now you just run a scanner generator. Now, as you can see now, the scanner generator says, firstly, I'm going to put an array, which happens to have 265 states. Then I'm going to apply a subset construction to get a DFA, which happens to have 139 states. After that, I'm going to minimize the number of states. I get a DFA with 106 states. Okay. This is the scanner generated automatically by the scanner generator. Check it out. It actually has, much longer than our kind of written one. And basically, this is the two-dimensional array including of the step.
What the fuck?
And this is the main loop. So basically, from here you can see every time you are in one state, you look at the next input character, you decide where to move. Essentially you just make all the transitions. The reason why this is long is for efficiency. In my slide it's only 20 lines. This one is for efficiency reason. Now, if we run this, compile this, remember this is our normal test case. It's just going to dump and obviously talking. Okay, that's fine. Do you still remember this example I used to explain the backtracking? Okay, so if this is the input given, we are supposed to return 1.2. There's the first token E, the second plus the third. We throw away the space and we return the last one. The point is that we do the backtracking. Okay, we start from one, and we wouldn't know which the first token will be until we are here seeing the blank space. Now you see how this guy works. See, that's the first token, that's the second one, that's the third one, that's a blank space, that's number 3 somewhere. Yeah, here. So that's 1, 1, 2, that's the second token, third one, and the last one. How does this guy does backtracking? This will not be in the exam, okay? So basically what this guy is doing is, if this is the input, okay, it's going to actually uses a variable to always remember the most recent accepting state. For example, if we start from 1.2, I will go here, now we realize 1.2 can't be accepted according to the DFA. So it remembers this position. Let's just run now, this position. And it just keeps going until it says plus, now it says a blank space. Now I realize we cannot go any further because 1.2e plus blank space is not a legal token. It needs to backtrack to the most recent accepting state. It has to remember that state in the strangely named variables that mark position here. Okay, so that you can use it. And if we edit that without a blank space, now obviously, one token here will be fine. Do you have any questions? My idea here is just to explain to you, number one, the theory behind regular expression in LDLA can be utilized for you to understand how to use a scanner generator and also how to write a scanner generator. Because in many universities, for example, a scanner generator is typically used as a final year project. It's like a thesis. The idea is not to re-implement a scanner generator that's already available in the public domain. Maybe just to implement generator, for example, a scanner generator for Rust, because there's not many efficient Rust scanner implementations in Rust. Or some people might want to investigate a different idea of compressing the static transition diagrams, just make it more efficient. It's just for final year project, okay, but not for a PhD project. Do you have any questions? Okay, so that's for this one. We're pretty much gone to that. Remember I said that regular expressions are limited because regular expressions cannot count. So that means you cannot write a regular expression to define the set of balanced parentheses. Okay? See in here approaches to infinity. That means you can never construct a finite state machine to recognize infinitely many balanced parentheses. Of course, you can do that for a finite set of balanced parentheses, but not for infinitely many. Okay? To do that, you have to use a safety. Okay? So a safety with 2 rules, I should be able to specify the balanced parentheses. That's simple because this guy is not a regular language. So this is a chart I showed you before. So basically, we have 4 types of grammars. In this course, we'll just look at SFT, regular grammars, which are equivalent to regular expressions. Regular expressions are equivalent to finite state machines. Context-free grammars are more powerful because it corresponds to stack automata. Okay? If you think about it, wherever you can make use of a stack, and it becomes more powerful than just the DFA, because the DFA only has a finite number of stacks. So that's all I want to say about today. Okay, for examination purposes, anything on scanner generator will not be part of. It's not examinable. It's not going to be a. There will be no questions, examination questions on scanner generators. However, it's just good for you to know, especially if you have done this course. However, it's absolutely necessary for you to understand all the algorithms you have to use to convert a given regular expression all the way into a minimal state DFA. And something I would like to say here. So there is a bonus assignment. You want to do it, you can do it. The bonus assignment I mentioned in the first lecture. It has 5 marks. But the 5 Y marks are added on top of your existing marks. For example, if your final marks without bonus assignment is 93. So there is a bonus assignment, you can do it. The bonus assignment, I'm actually pretty much the bonus assignment, I think the hardest part is to implement pointers. Okay? You figure out a way how to implement pointers. And all others, address operators, those are together, so that you will be able to write statements like this. Okay? Only one level of indirection, one stop, one ampersand operator. And so just 2 marks altogether, 3 marks. Function overloading is not trivial, because VC does not allow function overloading. You can easily extend your checker to allow function overloading. And function prototypes is something from C. For example, if you can have a function prototype, this program, the next rise will be otherwise, don't touch F. We don't know where F is, because F is still only starts from here. And if you have a function prototype, effectively you are extending the lifetime for F to here, from here all the way to the bottom, so that it becomes visible when you touch the T. And mixed iterations, every year there are students asking the same questions. Okay, so you look at the basic grammar, this is not allowed. Okay, you cannot mix declarations and assignments. That is intentional because to help students understand a CFG actually can affect the syntactical structure of the language defined. Right? So that's also not very difficult. So that's sort of bonus assignment is 5 marks. And if you want to do that, you can do that. Okay. Another thing is very surprising. Some students have trouble in using Java compiler compiling programs or using some third-party tools. And for every language, if you want to use a compiler, you have to tell the compiler where to look for certain things. Like library, for C, where to include the file are, you don't tell the compiler. I don't know where to look for. So certainly you must be aware of having the compiler. In Java, class is an environment variable. And you don't need to tell the Java compiler where to look for certain classes. I found that sense just like download that start using that straight away. So, especially since we are doing the compiler. So there's something a little bit rusty, you need to spend some time to develop better understanding of how to use languages and compile the system. Okay. So tomorrow I'm going to talk about table-driven error one parser. So in Assignment 3, we have implemented a recursive descent parser by writing a bunch of pass functions which call each other recursively. You can see that anything that's recursive can become non-recursive by using a step explicitly. Okay, so certainly there's another in that. And the second reason for doing that is by looking at how table-driven error one parser works, you will understand better about leftmost direction to see clearly why table-driven error one parser always discovers the leftmost direction, even though that's quite obvious for the recursive descent parser anyway, because every parser function applies one direction. Here it's just more clear. Okay, so there's something we can do. And next week we'll probably just have my preparation. We'll talk about Remember I said it was 15 minutes, but actually I some class 5 minutes. Sorry about that. Do we have questions? Alright, let's do more. So in this lecture, we're going to revisit syntactic analysis. So in this lecture, we're going to revisit syntactic analysis. There might be an opportunity to do something you did in order to implement a parser. So if you remember this chart, is in week 3. This diagram actually highlights the steps we follow to write by hand a recursive descent of non-parser. We start with CFG, which normally has 2 types of parsing conflicts, left recursion, comment prefixes. We need to eliminate both types of conflicts. That's something we did in assignment. You must be familiar with that since we have done that. Then you get a new grammar, G prime, which is free of these 2 types of parsing conflicts, then you do the first follow and select sets. So select sets are really defined in the first follow sets. So once you have done that, you can write a recursive descent parser by using from the parsing context introduced in the lectures in week 3. If you look at the red arrows, that's sort of the process we followed when we implemented our parser in the second and third assignment, because some 2 and some 3 really together with a parser. But this time, today, we can see how we can also get a parser differently. The reason for having a different way of writing a parser is very simple, because anything that can be done recursively can be done iteratively with an explicit stack. So that's why anything you can do in one way, you can do in another way. Okay? So essentially the process we're going to follow implements of the table-driven top-down parser is pretty much the same all the way, and so that we get the first one select sets, then the parsing table, which is really just a trivial representation of select sets. And we may use also the table-driven driver to do the parsing. So the driver has about 20 minutes. So essentially, if you want to do a table-driven parser, this is clearly something called editing. You just do limit that your product complex, get first follow sets, include your select sets with the parsing table, then you can use all these. You can use this 20-line long driver to do the parsing. Okay. So since the first few steps stay the same, I'll just show you the slide we had before. Now we'll go straight to the parsing table. I will show you how the table-driven parser works. The idea is that you see a different kind of driving parser. You have opportunity to revise something we learned several weeks ago, because the CFD's first follow says we will always be examining in the final exam. Might be opportunity to start revising this topic we learned already. So that's pretty much what I said earlier. Maybe a couple of signs. We have this equation saying anything that can be done recursively can be re-implemented by using iteration and also explicit stack. So basically, all the recursive calls adding a recursive design parser implemented manually can be implemented using stacking explicitly. Okay? And so if we take a look at the second approach for implementing a parser, you can get a better understanding of the whole parsing process. So this is basically how table-driven so-called R1 parser works, and we should be familiar with this jargon now. One L means we always input from left to right. The second L means the parser discovers the leftmost derivation. The Y means the parser makes use of a single token of the method. And if you look at the diagram below, this is where the scanner is, this is where the parser is. In a table-driven parser, the parser again is in the driver's seat. Wherever it is a new token, you just call the scanner token, and it makes use of the explicit stack to store the symbols, which are terminals and non-terminals. And then it consounds the parsing table, which is really a representation, a tabular representation of our select sets, to build a parse tree or to discover the leftmost derivation. Okay, so the so-called R1 table-driven parser generator simply works as follows. All you have to do is just to give the CFG to this guy. Okay, once you give the CFG to the table generator, this guy will be busy just doing the transformation to eliminate the two types of conflict, compute the first follow select sets, build the table, and then you get a parser automatically. So that's also why we did not ask you to run a parser by using the parser generator, because all you have to do is to give the CFG already available on our course website. Just simply give this to a table generator and you can parser. You don't have to do anything. It takes you 5 minutes to do it. Now, during this lecture, you should be able to understand how the table-driven parser generator works and how to use a parser generator in future when we use this unit. Typically, in practical applications, you will try to get a parser automatically by using parser generator. Again, we ask you to write a parser manually because that's better for learning purposes. Again, you have learned both reading a parser yourself. You're going to see how you can also use a parser generator to get a parser. But there are like error bar 1. And this one, the only difference is it discovers the rightmost iteration in reverse, but that's bottom-up parsing is not covered in this course. You really don't have to go. So this slide actually shows you how the error1 table-driven parser works. So on the top, you see the program, which is really just input data. At the moment, we see the input consisting of just A plus B followed by the EOF as kind of the file marker. You have a stack which keeps tracks of the symbols, terminals, and the non-terminals. That's where the driver is. Here at the bottom, you see the select sets represented by a parsing table. And what this parser will do is it produces the sequence of leftmost derivations discovered, and also build a parse tree at the same time. So essentially, you look at the sequence of production views, and you will realize that sequence actually represents the leftmost derivation. So this is really just a parsing program, the driver for the parser. And we take a look at this quickly, then we can trace the execution of this on a very simple program so that you can understand how the table-driven parser works very quickly. Okay? So if you look at the driver, they are only less than 20 lines of code. So we start by pushing dollar to the stack. The stack is initially empty. Then we also push the start symbol of the grammar to the stack. Then we enter into this loop. We repeatedly really do the same thing until the stack is empty. Okay? During every iteration, okay, we assume X is the symbol on the top of the stack. You will see what this means shortly. A is the look ahead symbol. That's really the token written from the scanner. That's how really a top-down parser works. Remember, X is the top stack symbol. A is the look ahead token. Then you decide what to do. There are really just two cases. If the symbol on top of the stack, if X is the terminal, you want the X to be the same as A. That corresponds to the match procedure used in our parser. If you still remember that. Otherwise, if X is a non-terminal, you need to predict which production to use. You don't have to do anything because everything has already been stored in the table. You simply just consult this table, and if this table contains a production for you to use, you simply just use that. Then you replace X by its right-hand side in the reverse order. You will see what this means shortly. And you have to reverse the right-hand side because the parser always discovers the leftmost derivation. Okay? So just to summarize, I'm going to go through example. Everybody will understand this. So essentially, you start with empty stack, you push dollar, then you push the start symbol, then you enter into this loop until the stack is empty. At any iteration, you look at the two symbols. The one on the top is X, the A is the token returned from your scanner. Okay, then you consider two cases. If X is terminal, that means X is token, you want X and A to be the same because that's the one we call the match in our parser. Otherwise, if X is a non-terminal, remember that's the time in our recursive design parser. What did we do then? So in the case when we implement our recursive design parser, if it's a terminal, we call parser X. Okay, so that we can recognize a language construct that's defined as X. And here we are doing exactly the same. Okay, if X is non-terminal, we need to see something that can be interpreted as X. We look at the table, we see which production can apply, then we simply replace X by the right-hand side in the reverse order, since we must always work on the leftmost non-terminal. When you reverse that, the leftmost appears on the top of the stack. Then at the very end, when you exit from the loop, the parsing process is successful. If the stack is empty, no errors have been recorded. That's the exact same as we did in assignment 3. Okay, that I'm going to go through example for you. So we're going to use the same grammar for our expressions, because this is how we do it. We start with G, the grammar will be limited after recursion, common prefixes. We get a new grammar, G prime, result. Those two issues, and with the first one on select says, and another with the layer. Okay? So grammar should look familiar to us. That's the classical grammar CFD, defining the traditional expressions. And that is the one we have seen many times without any left recursion. And this is the one we can write a top-down parser directly. Okay? So from grammar 1 to grammar 2, you need to eliminate the left recursion. This is something you did in assignment. So now we are only going to consider grammar 2 because we can only build a top-down parser for a grammar without any left recursion. These are some slides I took from week 3. Then you build first sets, then you build follow sets, the long-term nodes. Okay, not going to repeat what we did in week 3. Then you get your select sets. So select sets are defined so that you can know when each of these productions should be used. Okay? Again, I'm not going to say anything about how these select sets are computed. If you're rusty, you should go back to look at those slides from week 3. Okay, it would be very easy to use select sets in a table-driven parser. It would be a good idea to represent this in a two-dimensional table. This is very easy to do. On this slide, it's just one rule that tells you how to turn these select sets into a table which represents exactly the same information. Okay, I don't have to read this. I'm going to write this down very easily. So here are our select sets. Here is a table representation of the select sets. Okay, so here we see a table with two-dimensional. On the left-hand side, for each row, you write down all the long-term nodes. We only have 5, E, Q, T, F, R, F. And across the columns, on the very top, you write down all the tokens. Okay, we only have this many. That includes the dollar. That's the E or F. Okay, then you just turn each of these. You just view the table. How do you do that? is what it says. For each production, for all the edges in this guy, you set this to be. That production. So what that means is, let's just try a few. Now what is this one? So we just look at this production. How do we, enter the information for that select?
Have you ever taken lecture notes before? What's going on? I have the lecture here.
table, you look at the row indexed by E, that is the left side symbol, okay? Then you look at what's in the select set. It says select set of this production contains these two tokens. Then you just go to the table. Let me put it here. Then you just go to this table. Then you find the corresponding columns. Okay, one is int, then one is the left parentheses. Okay, then you just enter the production.
does epsilon get turned into the letter Q? do you make a table in Excalibur? Interesting. These are just icons. Stick. Why are you using that music? Okay, Control C, paste it into Excalibur and choose the charts. What the fuck? It's ludicrous. Is this just an SVG? What the heck? That's crazy. I had no idea that was a thing. That's pretty funny. I wonder what I would use it for. Yeah. That's crazy. Crazy feature. It's not what I'm looking for, but it's cool.
Okay, so we just look at the first production. E derives TQ. We want to enter the same information to the table. And we look at this table. We find the row that's indexed by E, which appears on the left-hand side. And this select set contains two tokens. So one is integer, other one is left parentheses. We simply just go to the table and enter these two production layers. So this would be E derives EQ. And since this set also contains left parentheses, we also enter this production here as well. Okay? So next time, if we are working on E, the local hand symbol is integer, or left parentheses, we know that is the production is not wrong. However, if you look at the table, we have omitted the left-hand side. That is simply because the left-hand side is already there, indexed by that row. For example, this row is indexed by E. Of course, the left-hand side symbol of that production must be always E. So instead of writing the whole thing, we have just omitted the left-hand symbol for that. Okay? Let's just that one. Let's just see one more. Now you look at the second. The second select set contains class. So that means if you're finding a leftmost derivation, if you're in the process of finding leftmost derivation, then you're currently dealing with Q. Corresponding to assignment 3, past Q is just being called. If you're working on finding what Q is, okay, then you want to know which production to apply. In this case, this select set says if the looker is a class, then you should just apply this. Okay? That information is actually here there. So if the looker is a class, okay, then we should apply this. Again, this is the production Q derives class Q, because the Q on the left-hand side is always the one on the same row next by Q. Therefore, we can overlap to write Q also very explicit. Okay? The third production contains the select set of the third production, and then minus, and we say we don't production contains the select set of the third production contains minus. Now we say if you look at this minus, you should apply this. Here's one more. Q derives epsilon. Okay, if you look at the select sets, it contains two symbols. One is a dollar, otherwise it goes in parentheses. Then you can see if you look at these two symbols, okay, we can apply this epsilon production. E derives epsilon. Okay? You can fill up this table this way by simply just applying this symbol. Okay? Every symbol in that set, you simply just set the corresponding entry for this particular production. Okay? That's it. So now we have a parsing table. So basically, if this is grammar given, this is grammar given, in the first step we eliminate its left recursion and common prefixes. This is grammar, it doesn't have any common prefixes, it does have left recursive productions. We do grammar transformation. Now we get grammar 2, that's free of those two issues. Then we get first follow and select sets. Now we're up to here. Then we simply represent all the select sets in a table equivalently. Okay? Then we can make use of this driver to perform the top-down parsing, so-called one table-driven parsing. Okay? So that's all the components. When we do that, this is the program being analyzed. We're going to make use of a stack which contains terminals and non-terminals. And by doing that, we are going to build a tree. At the same time, we're going to discover the leftmost derivations used for building that tree. During the parsing process, we are going to consult the parsing table to decide which production to apply. Okay? Everything is exactly the same as the recursive design parser including assembly domain, except that here we do not use recursion recursive procedures. We make use of iteration plus a step explicitly. Now, if you trace the execution of now for this expression, this grammar, we have just obtained a table-driven one parser, which consists of this guy and the table. That's it. Okay? Given this parser, if this is the input, I plus I, once I plus I, you can just imagine that we have an expression, something like 1 plus 2, because after lexical analysis, 1 will be written as integer, 2 will be written as integer, and plus will be written as plus. Because we always perform syntactic analysis on the tokens written from the scan. Okay? So if you run this table-driven parser on this given input, okay, if you trace this execution step by step, we sometimes going to off this slide. I'm going to show you how this trace is obtained. Then you can see that the parser can conclude successfully. This guy is a syntactic lead. Okay? This guy does that by making use of stack. That's the program being analyzed. That's the sequence of productions being used. That's the leftmost derivation found. That is the tree built incrementally. Imagine that's the tree build. Okay, so I'm going to go through this process for you. That will be really just the first part of today's lecture. Second part will be very quick. I will show you how we can use the parser generator to obtain a parser for this expression.